There we are. Good evening, everyone. This is Rich Ozer here. I'm here with Gerald McKeegan, who, there he is. And we're also honored to have John Curry with us tonight, who is assisting with all of the Facebook bugs and is doing a great job. So we're doing pretty well tonight. We've got a pretty clear sky. There were some high clouds earlier. They've cleared out. So it looks like we'll have an opportunity to look at some things through the telescope. Behind me is Nellie, our 36-inch research reflecting telescope. And we're going to be looking tonight at what, Gerald? What do you?
Well, I think we're going to look at a couple of planetary nebulas. Now, bet you I am now.
There you go.
Okay, so let me do that all over again. So again, this month Chabot is holding a virtual silent auction. It's to benefit STEM education. And you can bid on some of the photographic prints that were part of Chabot's Luminous Moon exhibition last year. These are high resolution images captured by NASA astronauts. There are also pictures taken with by satellites, pictures taken with Chabot's own telescope. And you can also bid on some really interesting experiences. For example, a dinner under the stars up here at Chabot. So we're going to paste a link in the comments section. And if you go to that link, you can bid on whatever device or whatever image you'd like to bid on, or whatever experience you'd like to bid on. We encourage you to do that. And again, this is to benefit STEM education. All right.
Did you want me to put a link?
Yeah, there was a link in the email to put on the
Okay.
comments section.
Yeah, let me see if I can find that.
Yeah, bear with us here for a few minutes. We'll get that link on the comment section. And I've kind of browsed through there. There's a lot of great images of the moon. And some of these are very high resolution and very big images too, suitable for framing on your living room wall or your office wall, wherever you'd like to put it. And then again, we have several interesting experiences you can also bid on.
All right. Not quite sure how I'm going to do this.
Maybe we can have John post it on there.
Yeah, I think we're going to have to. Yeah, I can't do this right now.
Okay.
It's
All
too
right.
many.
I'll
too
tell
many
you what,
records.
I'll send the link to John. He can post it on there.
Okay, that'll work.
All right. All right. Well, while we're doing that, maybe you can talk a little bit about the Ring Nebula.
Sure. Okay, so, whoops, let me get my audio on. There we go. So we're going to look at a couple of planetary nebulas tonight. And a planetary nebula, it's a funny name, Planetary Nebula, because it really has nothing to do with planets. But when they were first observed through small telescopes, many hundreds of years ago. I'm sorry, John? Oh, okay. When they were first observed through small telescopes many hundreds of years ago, there was some speculation that maybe they were looking at an additional planet that they didn't know about, because they tended to be spherical in view, and they had color, like bluish color. And in fact, there's one planetary nebula that I enjoy looking at called the Ghost of Jupiter. We're not going to be looking at that one tonight, but it's about the same size as Jupiter when you look at it through a telescope, and it's a nice bluish color. So people didn't know what it was, so they called them planetary nebula. What they are, in fact, are the remnants of stars that have aged out to the point that they've lost their outer shell of gas. And that gas has been blown out into space into a large kind of hourglass shaped structure. And what's remaining behind that from that event is the core of the original star, which is now a white dwarf star. And the brighter planetary nebula, if you're fortunate, you can see that central star glowing in the center of all of that gas. And that illuminates all of the different colored gases that are expanding out into space around that remnant of that original star. And so you sometimes get blue colors and red colors and green colors. And we're going to be showing you the Ring Nebula tonight. And you should be able to see a very distinct red color in that. It's one of the astronomical objects through modest telescopes where you can see some color. And we're also going to take a look at the Dumbbell Nebula, which is not far from the Ring Nebula in the sky. What's interesting about pairing these two objects is that the Ring Nebula, you're looking kind of down through the top of the hourglass shape. So it looks like a circle, right? And down inside that circle, you'll see the central star. The Dumbbell Nebula, you're looking at from the side. So you actually see more of that hourglass shape that I'm talking about. So let me see if I can share the, yeah. Stopped on where? Not just. Involving internet and telescopes. Yeah, we're struggling with some technical issues tonight, so you're going to have to bear with us. All right, I'm going to try to share the screen now.
Yeah, so what Richard was trying to explain is with the Dumbbell Nebula, we have a different view. Instead of looking down the tube like we are with the Ring Nebula, we're going to be looking at the axis. So it's as if you took the Ring Nebula and turned it 90 degrees so that you could see that there's two flared patterns of gas going out, and you can see the Taurus around the center of around the black hole at the center. So right now we're looking at the Ring Nebula here, and this is looking more or less straight down the tube of the hourglass.
I'm going to increase, this is from just a 10-second exposure, what you're seeing now, and I'm going to increase that to 30 seconds. So let's do a capture. And there we go. So for those of you that are seeing the 10-second exposure on the screen, you can see the reddish color in the outer part of that ring, and then a greenish color inside, and then a bright star in the very center, which is the central star of the nebula. And the reddish color is hydrogen gas, and it's part of the, yeah, that's much better. That's much brighter.
There you go.
The reddish color is indicating hydrogen gas. The greenish and bluish colors are oxygen. So a lot of important elements are formed from these events.
Now, even though it looks like there's a lot of oxygen there, actually in the entire cloud, the dominant gas is hydrogen.
Still hydrogen.
But oxygen, when it's ionized by ultraviolet radiation, which is what's coming off of the white dwarf at the center, the oxygen glows a really bright kind of turquoise green color, and it actually overwhelms the red color of the hydrogen. So a little farther out, you see there's more hydrogen, and so it's glowing a little bit red. But closer into the white dwarf, there is enough oxygen that it just overwhelms the hydrogen, even though there's actually more hydrogen gas there. Now, this is the fate of our sun. Our sun is going to go through a very similar process in about 5 or 6 billion years. It will first swell up, become more than 100 times its current size, which is bad news for the Earth, because when it gets that big, it's going to fry the Earth. But the sun will get much larger than it is now. When it gets really big, its gravitational hold on its outer layers will be very weak, and there will be much stronger internal winds. So it will begin to blow off the outer layers of gas out into space. That will go on for tens of thousands of years, maybe 100,000 years. And as that happens, the star loses its mass, it exposes the inner hotter part of the star, and then the fusion process will eventually stop, and that will cause the star to collapse into a white dwarf. And our sun will be surrounded by a cloud of gas, and it will be producing its own planetary nebula.
Mike asked, where in the night sky is this nebula? And it's in the constellation Lyra.
Yeah, if you go outside right now and look almost straight up, you'll see a very bright bluish white star. That's the star Vega, and it's the brightest star in the constellation Lyra.
Somebody mentioned fry the Earth is such an ugly term. You should have said energize the Earth.
Yeah.
That's a much nicer spin on the entire process. Yeah, I want to mention
it's going to destroy the Earth.
Come on, you got to put a positive spin on it. I do want to mention that the Ring Nebula is a good binocular object as well.
Yeah,
so if you have a decent pair of binoculars, you should be able to see it.
It won't look this big in your binoculars, though.
How far away is it? I want to say
2,300 light years.
Oh, okay, I was
give or take about
give
or take about 100 light years. It's 2,300 light years away.
No, Vega is not the star in the center of the Ring Nebula.
Yeah,
the star in the center of the Ring Nebula it's a very, very dim star. It's like 10th magnitude star. Vega is like a magnitude 3, I think.
Oh no, Vega is magnitude 0. It is.
Oh, magnitude 0.
It's the standard for magnitude 0.
I didn't even know that.
Yep.
So yeah, Vega is much brighter than the central star in the Ring Nebula. White dwarf stars are very small, and whereas Vega is a giant star.
Yeah, Vega is very hot. It's actually hotter than our sun. It's a relatively young star. It's spinning very fast, so fast that it actually sort of flattens itself at the poles.
So Violet was asking for more detail on what you were talking about. When a star ages and it starts to burn up a large percentage of its hydrogen fuel, then you start to get variability in the size of the star, because a star is a balance between heat and gravity. So you've got gravity attempting to bring all of the mass of that star into as small a space as possible, yet the heat from the nuclear fusion taking place in the core of the star is pushing all of that gas back out. And so our star is perfectly balanced right now. There's a certain amount of gravity pulling all of the material in, and there's a fairly consistent amount of heat keeping the gas at a particular diameter. So the star is not, our sun is not changing very much. But once that fuel starts to burn out and the whole fusion process becomes more variable, then it starts to expand and contract, expand and contract. And eventually that expansion starts to happen more rapidly and to a much greater extent. And that's when the star starts to slough off some of its outer material. And that's when it would essentially fry the planets that are in that material's way. So you can imagine a big shell of hot hydrogen gas being thrown off of the sun, and it would be speeding its way through the solar system, pretty much incinerating everything in its path. That will happen fairly quickly, right? It's going to be, you know, once that event happens, then it's a matter of you know, months, years, not like millions of years or anything like that.
Yeah.
So, but you first have to get through that, you know, that instability before it actually reaches the point where the material is thrown off the surface of the star.
Right. Yeah, right now the sun is fusing at its core. And if you looked at a cross section of the sun, all of that fusion process is happening down almost right at the center. Less than 10% of the size of the sun is where all the fusion is happening. Over time, that fusion process is converting hydrogen into helium. The helium settles to the exact center of the sun. It's sort of like the ash, and it falls to the center of the sun. And eventually the fusion process, which is still fusing hydrogen, begins to work its way outward towards the outer part of the sun. And this goes through several processes. Eventually it'll start fusing helium, which is when you start getting that fluctuation that Richard was talking about. And then potentially it can start fusing the helium into hydrogen and oxygen. And that'll be the end game for the sun. It doesn't have the mass to go any farther than that. So once it runs out of fuel at its core, it will collapse. But before that, it will have swelled up and become that giant star and losing its outer layers of gas.
Okay. So that whole process of fusing heavier and heavier elements is really the defining part of a star's you know, overall life cycle, and it stops at carbon, and that's when you get the, you know, the deep red carbon stars that are really kind of interesting to look at, and there's several of them in our night sky. Very deep red stars, almost you know, like what's the jewel I'm thinking of, which is the deep red one?
Ruby?
Ruby, yes,
Yeah,
ruby
yeah.
colored. Yeah. How old is our sun? Farrell, do you want to answer that? Age of our sun?
4.567 billion years. It's an easy number to remember. 4.567 billion years. And it will survive probably to be 11 or 12 billion years, but those last billion years are not going to be very pleasant. It's not really spinning, it's expanding. So the question was, how fast is the nebula spinning? It's not really spinning, it's expanding outward. In a minute, when we look at the Dumbbell Nebula, you can actually see that gas is being blown off primarily from the poles of the star, and the gas is expanding outward In fact, one of the ways we figure out how far away this is, because we can't use more traditional techniques for measuring the distance, one thing we can do is spectroscopically measure the velocity of the expanding inner shell of the nebula, and observe that over time and see how much it changes. And because we know how fast it's going, we see how much of an angle it changes over time. And you can use that to compute the distance. And so that's one of the techniques they use to figure out the distance to the nebula.
One of the things I should mention, I was just thinking, I'm muted. One of the things I was thinking about now is several people may not have tuned in over the last few weeks, but may have seen us earlier in the year. I did change the software that we're using for this. Started to use a great program called Backyard EOS that's designed to work with Canon DSLR cameras. And this one seems to do a much better job of not only displaying what we're seeing off the telescope, but gives me a somewhat more responsive adjustment points as well. So I'm really happy with the result of this. It really looks pretty good. So Backyard EOS is a commercial piece of software. It's not very expensive. If you own a Canon or Nikon DSLR camera, it's a great way to hook up your camera to a telescope and download the images to your laptop and control all the different features of the camera at the same time.
Can you show just that portion of it on Facebook? Because it's just very small.
Oh, which portion?
You're seeing your whole desktop.
Oh, just the image?
Just the image.
Oh, yeah, we could do that. Let's try that. Let's see what it looks like. There we go.
There you go.
Let's see how that looks. I've been watching how it appears on Facebook as well.
Yeah, so you can see the central star, the white dwarf. It's that little faint star right in the center of the donut hole. By the way, this thing is huge. The part that you see there is a light year across. So basically you can take all of the planets in our solar system and tuck them right into the donut hole and still have room left over. And what you're seeing is not all of the cloud of gas. There's actually a lot more gas extending farther out from the nebula, but it's hydrogen gas, and it's cool enough to where it's not really glowing very brightly. If we were to put a certain kind of filter on the telescope or on the camera and take some very long exposures, several hours worth, you would actually be able to see that the cloud around the star extends much farther. In fact, it might actually extend beyond the frame of the image here. So lots of hydrogen gas coming off the cloud, or the star.
I want to say hi to Branson. Hi, Branson. Thanks for watching.
He's just 5 years old.
Yeah, he's 5 years old. Make it even bigger.
Yeah, it's off center though, so
it is off center, but that's okay. It's, you know, it gives you kind of an interesting perspective on it. Again, people were asking, is Vega in this? No, Vega is pretty far away from the line of sight of this object from the perspective of the telescope. So it's several degrees off.
Yeah, if we pointed the telescope at Vega and took a picture, it would be so bright it just about wash out the image. So,
oh, it would totally bloom the image.
Yeah. Vega is a really bright star. We have a magnitude system that we use for measuring the brightness of stars, and Vega is actually the standard for that magnitude, or one of the standards for that magnitude system. We used to think that the brightest star was at magnitude 0, and then a little bit dimmer star is magnitude 1, and dimmer still is magnitude 2, and so forth. Vega is considered to be the standard for magnitude 0. So next time you're looking at Vega, kind of register it in your head that you're looking at a magnitude 0 star.
I don't know how I never knew that. That's a great piece of
Yeah,
information.
yeah.
Somebody was it is.
Yeah.
Somebody was commenting that they're now hungry for donuts.
Yeah, we have a lot of fun with the kids when we're looking at Ring Nebula through the telescope. We often tell them to look through the telescope and find the fuzzy donut. Or the ghostly Cheerio, the fuzzy donut, the fuzzy Fruit Loop.
So what do you think? You want to give a shot at
Yeah, I think why don't we plan on going to the Dumbbell Nebula, which is actually a similar nebula, but we're looking at it from a different angle. So let me get that set up. And Richard, you're muted right now. All right, I want to make sure.
Daryl's got to go through the process of moving the telescope. And here, I'll put it back on brighter image.
Yeah, we're not going to move a whole long distance, but a little bit.
Oh yeah, thank you. Yeah, we had a small accident a couple of weeks ago. We don't want to repeat it.
Was it M27, right?
M27.
Yeah.
Yeah, M27 is the formal designation, and the M in front of
Here we go.
these objects means that they were cataloged by Charles Messier.
Constellation is it? We're starting to get some cloud.
Yeah, so let's get on this. Yeah, those clouds have been coming in.
On the edge of the clouds.
Yeah. All right, now let's see. I'm going to take some quick 5-second shots to see whether it's in the field of view. Yeah, perfect.
All right.
All right, so let me stop it and take longer exposures.
Yeah. Now, because we're looking at it at a different angle, the gas appears to be more diffuse. It's actually closer. In fact, it's about half the distance that the Ring Nebula was. So the Ring is about 2,300 light years away. The Dumbbell Nebula is somewhere between 1,200 and 1,300 light years away. So quite a bit closer. But because of the different angle, we don't see as much concentration of gas, which makes it look more diffuse. But it's a much bigger object because it's closer. So you're shooting what, a 10-second or 20-second? So Richard's taking a 20-second exposure here. There we go. You good? Oh, is it stacking them?
No, I'm not doing stacking.
Oh. So you can see the two lobes on either side. If you look carefully, you can see the white dwarf at the center, basically where the two triangular lobes, the apexes meet. That's the white dwarf. And now you can see that the gas is coming kind of off the poles. There's also a Taurus around the equator of the star, which is not very distinct in this image. Some of the longer exposure images that we might do, it's more distinct. And again, this is gas that was expelled before the star collapsed into a white dwarf.
You know, I don't see why not here. I'm going to try increasing the exposure to 30 seconds.
Okay.
Get a little more color.
Constellation is that in Aquila?
It's in Cygnus. Actually, it's in Vulpecula. Vulpecula is the fox.
Is that how that's pronounced? You say it Vulpecula, but Vulpecula is probably.
I don't know.
I always call it Vulpecula.
Yeah, it's the fox.
Now I got to look it up.
It's between Vulpecula, whatever you want to call it, and Sagitta. Sagitta is the arrow. Vulpecula is the fox.
Okay, there we go. Got a little more data here.
There's a great binocular object in Sagitta. It's called the coat hanger. And it's one of the first things I ever looked at when I was a kid, getting interested in astronomy. So I had a pair of binoculars and I read about this thing called the coat hanger. So I started looking for it. And when I saw it, I was amazed. It looked just like a coat hanger out in space.
I want to point out a couple of things here. So you'll notice that at the very top here and at the bottom, you see the red that I had been talking about earlier that indicates hydrogen. And in the center, you see the green and blue that shows the presence of oxygen. And you can imagine turning this whole thing 90 degrees and comparing it to what you saw with the Ring Nebula. And the red would be forming a circle in a wider circle than the green would be forming. So if you were looking down this tube, if you were like where this star is, looking down towards the central star, it would look an awful lot like the Ring Nebula did.
Now, there are a lot of planetary nebulas out there. This is how most stars end their lives. And there are a lot of planetary nebulas out there, and they often have very spectacular looking patterns of gas. A lot of them are in an hourglass shape, and whether you're looking down the tube or at an angle or looking from the side, some of them look almost like a butterfly pattern. It just depends on how vigorously the star expelled its gases when it was a red giant.
All right, Teresa, I'll try putting it on full screen again. I have a feeling it's not going to look that great on full screen because it's not as bright an object, but we'll try it. Yeah, good. It looks kind of dreary and blurry.
Can you unzoom it a little bit?
Yeah, maybe that'll work. Oh yeah, there we go.
There you go.
That's not too bad.
Yeah.
Okay, let's see what it looks like. Everything on Facebook is 30 seconds delayed, so I'm looking at it on my screen now, and you guys are 30 seconds behind me. Yep. Yeah, there we go. That's pretty good. All right, we'll live with that. You're very welcome. Yeah, okay.
All right, I'm not sure what else we can tell you about the Dumbbell Nebula.
I could say a couple of other things about it. I've been doing a lot of photographs of this nebula myself, and I'll tell you why. I try to do astrophotography with I have an 11-inch. Oops, that one got something moved.
I didn't do it.
You didn't do it? All right, we'll see if the next one looks right. That was strange. I have an 11-inch telescope, and to get a frame that looks like this is usually like a 5-minute shot, not a 30-second shot, right? But I have a set of what are called narrow band filters in order to pick up the hydrogen and the oxygen and the sulfur bands of light. And when I installed them in my camera, it was like back in November. And then, you know, everything happened between November and March, and our whole world turned upside down. And I had forgotten what order I put the filters in my camera. And one of the cool things about the Dumbbell Nebula is that the image from hydrogen and the image from oxygen and the image from sulfur are so dramatically different that you can use that as a way to figure out what order you put the filters in your camera. And so I was taking shots of this several weeks ago just to figure out what I had done several months earlier, and it worked out very well.
There's a comment about asking
Yeah.
about the stars in and around the nebula.
Yeah.
They really don't mean anything. They're
Yeah.
Right. They're mostly background
mostly
stars.
background stars.
The one that you see right at the center, if you can put your cursor on the one right at the center, which looks a little bit bluish white, that's the white dwarf. So
We're getting clouds now, so I'm going to
Yeah,
reduce the
yeah.
Oh, yeah.
yeah, that's why it was getting washed out.
right.
Yeah, so the stars certainly make for a more interesting image, and but they're not actually the only star that's really associated with this nebula is the one that's right here in the center where my cursor is, because that's the central star of the Dumbbell Nebula. All these other stars around it, they're just either foreground or background stars that are nowhere near the actual nebula.
No.
Yeah. Yep.
Looks like clouds got out of the way a little bit here.
Yeah. Now I'm going to keep it at a lower zoom level
Yeah.
just for now.
So probably 90% of the stars that you see in the night sky will end their lives like this. There's a common misconception that most stars blow up in a supernova. That's actually not true. Most stars die this kind of slow death that you see here. It's only the massive stars that die in a supernova. So a star that has maybe 8 or more times the mass of our sun will end its life in a supernova explosion. It goes through the same expansion process when it gets old, but because it has so much more mass, it can continue the fusion process well past the carbon and oxygen stage and continue into much heavier metals. Eventually, it produces an isotope of iron called iron 56, and iron 56 can't fuse anymore. And when it reaches that point, the fusion process stops at the core. The massive star collapses on itself and then explodes, and that's how you get a supernova. So that only happens to stars that are 8 or more times the mass of the sun. Most stars are much smaller than that.
Question was, why is it called the Dumbbell Nebula? So it kind of looks like a barbell, right? And it's like right here where the cursor is would be where your hand goes, and then these are the weights on each side. And another term for a barbell is a dumbbell, and that's why it was named that.
Right. Actually, it goes back to William Herschel is the first one who likened it to that. They had a different term for the dumbbell weight that you see in a gym back in the 17th, or I'm sorry, the 18th century. So William Herschel gave it that name, and then as they began to call that device a dumbbell, then it became the Dumbbell Nebula.
Yes, I first heard the Dumbbell Nebula, and I thought they had named it after me.
Oh.
All right. You know, we do have a pretty clear view of the planets tonight.
Yeah, so let's go to
You wanna try
Jupiter,
doing that?
maybe?
You want to try doing Jupiter? Yeah, we'll give it a shot, folks.
All right. Let's go to the planets.
And those I will do live. That's a whole different process here. So.
All right, here we go. We may have to adjust it a little bit once we get there.
Oh, I'll definitely have to do it on my end.
Yep, it's in there.
Okay, John, you want to help me get that centered? Oh, Gerald's got it. All right. Let me.
Oop, wrong way.
All right, I'm going to have to do this a little differently.
Okay, so there's Jupiter. You can see one of its moons off to the left there. And now you see Jupiter by itself. By reducing the exposure so that we can see Jupiter clearly, we kind of,
Yeah, oh, you want to talk about the moons? I can bring it back to where it was. Yeah, if you want to see the moons, I have to overexpose Jupiter.
Yeah.
So let me get that back down to a.
What's interesting is that the dynamical range of the human eye is much greater than the camera. So when you look through the telescope, if we put an eyepiece on the telescope, and when you look through it, the planet is very clear, as are the moons. You can see the moons and the planet, and you don't have to go through this overexposure process. But you see a moon just to the left of Jupiter, and I believe that's Io. Then there's, I saw one before we moved the telescope, there's one way off to the right.
One way off to the right and to the left. Ganymede is to one side.
Yeah, we don't have them in the field of view though. So
yeah,
all
unfortunately.
right, so let me go back to so we can see some detail on the actual planet here.
So Jupiter is much bigger than the Earth. It's 11.2 times the diameter of the Earth. So it's really big. It's a gas giant, so it does not have a solid surface. It's just a big ball of very dense gas. In fact, it's so dense that deep down inside, and by the way, the gas is mostly hydrogen, deep down inside, the hydrogen gas is almost liquid in appearance, and the atoms of hydrogen kind of get lined up, and the electrons start to flow freely. And so hydrogen in that state is actually electrically conductive. So what we say is that it's metallic hydrogen because it conducts electricity like metal does. And I think I'm seeing the great red spot there. Is that what I'm seeing?
No, we're not.
No?
I'm not seeing the red spot. Definitely seeing the cloud bands.
Yeah.
You know, this is the usual thing that this is their usual affliction here. Is the planets are fairly low in the sky, and the seeing tonight is not great. And when we talk about seeing, we mean the amount of atmospheric distortion caused by, temperature fluctuations in the atmosphere. And it actually causes the atmosphere to act kind of like a lens, right? But that's constantly changing. Right. So things get sharp and blurry and sharp and blurry. And depending on how still the atmosphere is, that's going to determine how clear the views from the telescope are going to be.
I can clearly see the bands in the finder, but it's jumping around like crazy.
Yeah.
Yeah, we got a lot of turbulence. Plus, we've got that cloudiness that's still going through.
Yeah, but nonetheless, at least you can see the cloud bands. Those are pretty. Gerald, I think you're right. I think the red spot is like right here where I've got the cursor right now.
Not according to Starry Night.
No?
Yeah, the one I was seeing was actually
Starry Night, because I just saw a big red blob show up there, but it's probably an artifact of the sea.
Yeah. Now, what some astrophotographers will do, rather than using a digital SLR camera, they'll put a video camera on the telescope and just shoot video for several minutes. And they end up accumulating a lot of frames, thousands of frames. And because it's constantly going through this process of being real sharp for a split second and then fuzzy and then sharp and fuzzy, you go through those thousands of frames and you find, maybe the 20 or 30 that are really sharp. And then you combine those to produce a pretty sharp image of the planet. But you got to have a lot of patience to do that, and it takes a lot of skill. But
yeah, you're mostly going through a movie frame by frame and throwing away 90% of the frames, and then taking those last 10%, stacking them up, and then enhancing it. You'll spend a day, at least doing that. But there are some individuals who have mastered this process to such a degree that their photos are almost indistinguishable from a spacecraft taking images. If you look up the photos of a gentleman named Damien Peach, and his last name is spelled just like the fruit peach, go ahead and search for him. Google Damien Peach, and the other person is Christopher Go. Both of these guys are phenomenal at stacking planetary video, and their results are mind-boggling. Every time I look at their photos, I think, why do I bother? They have really mastered it, and they travel to places where the seeing is really good. I think Damien Peach, he likes going out to the islands south of Florida, where the airflow is always very, very steady, and some of the islands, like he goes to like the Bahamas and places like that, where the land is very flat and there's very little turbulence, and you get a very steady stream of air, so you get what's called laminar airflow. And he'll do significant travel to find places that have just the right atmospheric conditions to take those photos.
Well, he does a lot of it from his backyard as well. He lives in England, and he does a lot of it from his backyard. His backyard telescope is the same telescope and mount that I have. And when I first learned that, I saw how great his images were, and I found out he was using exactly the same telescope and mount setup that I have. I thought, I don't know how he is doing that. There is no way I can do that with my telescope.
Yeah.
So anyway, the planet is huge, and it's a gas giant, and it's rotating very rapidly. A day on Jupiter takes 9 hours and 50 minutes, give or take. So less than half the length of a day on the Earth. And you think about it, you've got a planet that's 11.2 times the diameter of the Earth. It's roughly 88,000 miles in diameter, and it's spinning more than twice as fast as the Earth is. So that produces really strong, very rapid winds, especially near the equator. And, it's a gas giant, has an atmosphere, and that atmosphere has high and low pressure areas in it, just like on Earth. But unlike Earth, on Earth, the high and lows, they kind of swirl in these little swirly patterns that we see when you watch the weather. On Jupiter, those highs and lows literally wrap themselves around the planet, all the way around the planet. And that's how you get these dark and light colored bands that you see. The dark colored ones are actually low pressure areas that have wrapped all the way around the planet.
It's a very energetic planet too.
Yes.
And one of the interesting things I learned about Jupiter a few years back at the Geophysical Union Conference was the interaction between Io and Jupiter is very significant. Now, Io, which is the moon we were showing you a little bit earlier, has a lot of volcanic activity and has several volcanoes all over the surface of the moon. And the lava that comes out of those volcanoes ends up getting accelerated by Jupiter, and the material turns into a plasma. And so there's a torus around Jupiter. It's called the plasma torus of this material that originated on Io and essentially gets accelerated to very, very high temperatures, very high speeds, and travels in a donut shape around Jupiter. And it's kind of like as if Jupiter was acting like an accelerator. And all of that activity is fed by the material coming out of Io's volcanoes.
Yeah, Io is actually the most volcanically active body in our solar system. Io orbits very close to Jupiter. Its orbit takes just under 2 days. And because of that, its orbit is highly elliptical. Because of that, as it gets closer to Jupiter, Jupiter wants to actually stretch the planet because of Jupiter's strong gravity. And then as it moves away from Jupiter and in its elliptical orbit, actually the opposite happens, and that actually the stretching weakens. And so what's happening is as Io goes around Jupiter, it's stretching and then release and stretching and release. And that creates a tremendous amount of internal heat in the planet. And that's what causes it to be so volcanically active.
Well, we can give Saturn a shot if you feel like it.
Yeah, I wanted to try something here.
Oh, sure.
I don't know if I can share my screen or not.
Yeah, go for it. You should be able to.
Let me get back to Zoom here. No, I think I'm good. All right. Yeah, okay. So this is an animated GIF image taken by a spacecraft that flew by Jupiter. It was actually, I believe, the Cassini spacecraft. When it flew by Jupiter on its way to Saturn, it took this image. And you can see the plume of a volcano up near the top of the image. That plume is actually about 200 miles high. And you see all those other dark spots all over Io. Those are all volcanoes, and as you can see, it's an extremely active body. It is the most volcanically active in our solar system. All right, back to you, Richard.
All right. Why don't we try slewing to Saturn?
All right,
And,
all right.
see what we get. I have to share my
Still
screen
more or
again.
less clear that way.
There we go.
Hey, there it is, right in the middle. All right, so Saturn is much farther away than Jupiter is. Jupiter's distance from the sun is a little over 5 times the Earth-Sun distance, what we call an astronomical unit. So an astronomical unit is the average distance between the Earth and the sun. It's a little less than 93 million miles. Jupiter is 5.2 astronomical units away from the sun. Saturn is 9.5 astronomical units away, so it's quite a bit farther away. Saturn is not quite as big as the as Jupiter is. It's about 9 times the diameter of the Earth instead of 11. And then the distance across the rings, is about 300,000 miles, a little less than 300,000 miles. So I think Richard is trying to adjust the.
That's about as good as we're going to get.
Yeah, we don't see Titan.
No.
It's there, but just it's probably about right here.
Yeah.
Yeah, that's about as much as I want to magnify it to right there.
No, you'd have to shrink it down.
No, I'm not talking about Titan. I was just talking about the planet.
Yeah.
No, Titan is just not in the field.
Right.
So you see even more here the effect of the turbulence in the air. It's just going in and out of focus. The rings of Saturn are ice, mostly small chunks of ice. You might occasionally find one in there about the size of a refrigerator, but most of them are much smaller. In fact, some of it is almost dust-like. And the ice is what looks to us like only 8 rings. If you get up close, you actually see that there's millions of rings there. In fact, I think while you're doing that, Richard, I think I'm going to see if I can find us a picture of the rings, close-up image of the
Yeah, that
ring.
would be great. While you're looking at that, Manju had asked, getting back to nebula and supernova and all that stuff, what a nebula and a supernova are two completely different things. They're not. There's some relationship. One leads to the other, but they're different. They're different phenomena. They're different objects. So a supernova is what happens when a star cataclysmically explodes because it's got so much material that it collapses on itself, has a massive explosion, leaving behind usually a neutron star. And that gas that comes off of the explosion and gets shot into space, that ends up becoming a particular type of nebula. And there are several nebula that are visible to us in our own Milky Way galaxy that are the results of supernova. The most notable one is the Crab Nebula, which if you look that up, Google the Crab Nebula, and it's one of the finest examples of what a supernova remnant looks like. The other is there's the Veil Nebula, and there's several others, but Crab Nebula is the best example of a nebula that originated from a supernova explosion. But there are also many other types of nebula. Nebula just means cloud of gas. So there's other types of clouds of gas that have nothing to do with supernova. So I hope that helps.
So if I can share my screen again, Richard?
Yeah, go for it.
I've got an image here.
Do I have to give you permission, or are you set?
I think I'm good here. Okay. All right. Everybody see that?
Oh, that's great.
Okay, so the Cassini spacecraft was a very large, it's one of the largest spacecraft ever sent to a planet. And it orbited around around Saturn from 2004 until 2015. And it orbited in different directions. They changed the direction every once in a while. And it took some just spectacular images of the rings of Saturn. And you see in this image a lot more detail of the rings. And you can actually see that in some cases, what looks like dark or gaps in the ring are actually just darker regions where the ices are less dense. But you can see that the rings are actually composed of hundreds of individual rings. When you orbit around a planet or a star or whatever you're orbiting around, the farther away you are, the slower you orbit. So you can't have a continuous band of material all orbiting at the same speed. So material that's in close to the planet, for example, the lower right corner of this image, those ice particles are orbiting much faster than the particles that are in the outer part of the ring. And because of that, there's some shearing that goes on. And so the rings sort of divide themselves up into mini rings that you see here. And this really very well illustrates the point. Got another one here. Let me unshare and change.
Questions?
All right.
No, it's not possible to walk in the ring. When the rings were first observed, the initial thought was, oh, they have to be solid, right? Because they kind of look solid, right? And that would be kind of neat if they were, but they're not. And it would be a terrible walk. And cold.
Yeah.
Yeah, very cold. Yeah, it's already been 5 years since Cassini ended.
Yep.
Yeah.
Time flies when you're
Somebody said
having.
you could walk your dog alongside if you'd like.
So I'm going to share again here another image.
Say what?
I'm going to share another image
Okay.
here.
I'll leave it. Give it back to Gerald here.
All right. So if you look, this is a close-up of one of the outer rings. And if you look carefully, you see what looks like little ripples there. There are actually small moons within the rings. And those small moons have enough gravity that they actually distort the particles that are within the rings and cause them to either rise up above the ring plane or a little bit below the ring plane, and they create these ripples. And what this really illustrates is the thing I was telling you about before, about how the closer you are to the planet, the faster you orbit. If you look carefully, you can see that the ripples that are on the side of the rings are closer to the planet are all off in one direction relative to the mini moon, which is kind of hard to see, but it's in there. And then the ripples farther out on the outer part of that gap, those are going in the opposite direction. And that's because the orbital velocity of the particles closer is faster than the orbital velocity of the particles that are farther away. And when you have a little moon in the rings, it creates that little gap, and it disrupts the particles, the ring particles. The ring plane is only about, it's actually less than 100 meters thick. So it's actually pretty thin. So that's a nice image. And this is another Cassini image.
Yeah, a lot of good questions. Yeah, I couldn't remember how thick they were. I knew they weren't very thick. 100 meters is really thin. And I guess that if it was much thicker than that, Cassini would have had a hard time traversing the ring system like it did. And that was one of the nail biter parts of the mission, was when they actually passed through the plane of the rings.
Yeah, here's an even better shot of that same object here. And they took these images at a particular time. Saturn's ring plane is tipped relative to Saturn's orbit around the sun. So most of the time when we see Saturn, the ring plane is either tipped up in one direction or tipped down in a different direction. But every 15 years, I believe it is, the ring plane is seen edge on, and it's edge on to the sun. And when that happens, anything that protrudes above the ring plane casts these really long shadows. So you can see the long shadow of the moon that's within that little gap there. And then again, you can see how the inner part of the rings, the ripples are off in one direction, and the outer part of the ring, the ripples go in a different direction. And that's because of the differential velocity of the particles as they orbit Saturn.
Yeah, this is a much better photograph. It illustrates what you were talking about much better. Yeah, I like this. Are the rings mostly made out of water, ice, or rock, or all of the above?
Mostly water, ice, but some rock as well. But it's mostly water, ice. We think it was the result of icy moons that got too close to Saturn, got within what's called the Roche limit. If you're inside the Roche limit, if you're a not rigidly compacted object, the differential between gravity on one side of you and the other is enough to actually tear it apart. So we think that's what happened here.
All right, let me put it back on the planet here. Oops,
Where we go?
disappeared. There it
There
is.
it is. All right. Well, there was another object I wanted to show you, and it should be up by now. And it's a very different object.
What's that?
M15.
Ah, okay.
So we need to kind of do a couple of short slews to keep the telescope synchronized as we go off in that direction. So I'm going to slew here, and we're going to see a star. We'll center on that star, and then we'll slew again. Here we go.
Pegasus?
Yeah, we're going to go to M15, which is off the nose of Pegasus.
Okay.
Okay,
John,
so
there's the
we're
star
on a
right
star now.
That's,
Close now.
yeah, the star's up here, so yeah, go ahead and
Where is it?
yeah, hit north.
Okay.
That's good.
That's good. That's good. All right, I'm going to sync on that. And then we'll go over here to M15.
Okay.
Might need to do a 5 or 10 second.
Yeah. Let me go ahead and get some.
So the object we're looking at is called M15. It's a globular star cluster. Now, if you've been watching us over the last few weeks, we've looked at some other globular star clusters, M13 and M3 and so forth. M15 is a little bit different. M15 is what we call a core collapse globular star cluster. It has a mass that's roughly the equivalent of 450,000
Nice.
solar masses. In other words, 450,000 times the mass of our sun. And it's very, very dense at the core. As you can see in this image, it's very dense at the core. And so we call this a core collapse cluster. So the stars in the cluster orbit around the cluster in highly elliptical orbits that take it in close to the center and then far out. What's happened here is that some of those stars are no longer going far out. They're still in elliptical orbits. They stay relatively close to the core. Because the core is so dense, the gravitational pull of the cluster actually extends pretty far out. And the stars that orbit around it and go out far actually go very far out. They can go 200 light years out from the core, which is more than most globular star clusters. We're not sure about why it's so dense at the center, but there is strong evidence that there is an intermediate size black hole at the center. So an intermediate size black hole might be a couple of hundred solar masses. The space in the center, just to give you an idea, 10%, or I'm sorry, 50% of the total mass of the cluster is within 10% of the size. So the inner 10% of the cluster houses 50% of the mass. So it is really dense near the core. And that leads us to think that there is an intermediate sized black hole there. We haven't yet proven it, but there's pretty strong evidence. So this is called a core collapse globular cluster. It's different than M13, which is a nice big globular cluster that is not a core collapse cluster. M15 is about 33,600 kilometers, 33,600 light years away.
You've been accused of being obsessed with M15, Gerald.
It's true.
I'm kind of obsessed with it too. It's actually my favorite globular cluster to look at.
Yeah. It's one of the easier ones to find.
Yeah, that's why it's one of my favorite.
Yeah.
It's quite bright. And yeah, it is in the constellation Pegasus. So yeah, there is no galaxy Pegasus. It's Pegasus is a constellation, of course. And M15 is inside the Milky Way galaxy.
All right. Well, it's 10:41 here, so I guess we'll take a few questions and then wrap her up.
Sounds good. Yeah. Yes, we are all in the Milky Way galaxy.
Yes. Yeah. Now, the globular star clusters orbit outside of the main disk of the galaxy. If you're outside of the Milky Way galaxy, you'll see that it looks like a flat disk with spiral arms in the disk and a central bulge in the middle. The surrounding that is a region called the halo, and the globular star clusters orbit the galaxy in the halo.
Rob wants to know what our various backgrounds are. So, Gerald, how'd you learn all this stuff?
Everything I know I learned from Star Trek.
Yeah, that's true for like all of us, right?
Yeah, I actually got interested in astronomy, actually more in rocketry and space travel when I was very young, back in the 1950s. In fact, if you ever see the movie October Skies, I identify with that a lot because it's very similar to my childhood. I was very interested in rocketry and space travel. I was one of those guys who was out there standing in the middle of the street in 1957 when Sputnik was launched, and we were all standing out there trying to see it in the sky. In 1962, I built a rocket to shoot down Russian bombers during the Cuban Missile Crisis. So it was only about 3 foot long, but I was convinced I was going to be able to shoot down those Russian bombers. So then, eventually I went to work in the space industry. I got a master's degree in space studies, and I've been an amateur astronomer. I can't say I'm much of an astrophotographer, but I do like looking through the telescope at different objects. And since 2008, I have been the lead investigator, if you will, for the asteroid search and tracking program here at Chabot.
Yeah, live long and prosper. I'm purely an amateur. You had a lot of experience, Gerald, actually working in the space industry. I built my first telescope when I was 14 years old, and have been interested in astronomy since I was very young, and went on to build bigger telescopes than the one that I built when I was 14, and then got involved with the Telescope Makers Workshop here at Chabot, and for several decades have been one of the directors of that program, and now have a pretty solid interest in astrophotography. I've combined my day job, which is computer science, with this hobby, and have definitely enjoyed taking it in that direction, especially since my eyes are not what they used to be. And so, oh, was there? What was the question?
Well, you built it? Question mark.
Oh yeah. No, the one I built when I was really young was a simple refractor, and basically using a chunk of sewer pipe and some lenses from Edmunds Scientific, and a very primitive focuser and an equatorial mount made out of water pipe. And I still have that. It's somewhere in my garage, and it didn't even have a finder scope. It had a yellow stripe down the length of the telescope, and he would aim the telescope by sighting along the yellow stripe. But since then, I've built several larger telescopes. We teach people how to grind telescope mirrors here at Chabot. We have a telescope maker's workshop. Obviously, that's been closed because of COVID-19, and it won't be till next year that we're able to open that up again. But we're able to build some, fairly serious instruments for personal use using that method. So anyway.
Other questions?
Somebody was mentioning, Joe was mentioning that he misses Paul Zurkowski, who used to run the telescope makers workshop.
He was your predecessor, right?
Yeah, he was our predecessor. Paul's still around. He lives in Livermore, and I haven't talked to him in a few years, but he's still with us. Is there any software that allows you to see the sky as it would look from another place in space? That's an interesting question.
Yeah, there is. Yeah, Starry Night will do that.
Really?
Yep. You can go to different locations in space. I actually use that feature quite often.
I had no idea.
Yeah.
All right, Starry Nights it is. Great question.
Yeah, I think the current version of the sky will do it also.
Is there any dark matter in the solar system or nearby in our part of the galaxy? Probably.
Probably, but you can't see it.
But how would you know? Yeah.
See, we can answer yes, and there's no way you can prove it's right or wrong.
We can't prove that we're right, and you can't prove that we're wrong. This is out of topic. Nothing is out of topic. This is out of topic, but when will be the next comet that we can see with a naked eye? Who knows? These things are discovered not long before you're able to see them naked eye, right? So most of these comets, like Neowise and linear comet linears, these are all discovered by automated systems. That's why they have these kind of strange names. It's not like there was a guy named Neowise.
There's actually
it's not like the good old days when you had Halley's Comet. That was named after a person. Now
they still
Hale-Bopp, right? Now they're named after robots. But
there's still a few that get named after people, but
not too many. Though.
But just as an example, we had Comet Neowise back in July that everybody was watching and taking photographs and everything. It's kind of gone, and it's too far away now. But there was just a brand new Comet Neowise just announced today. Unfortunately, it's not as big, and it won't get as close, and it won't be as bright. So it won't be something that's quite as entertaining as the previous Comet Neowise, but both of those comets were discovered by the Neowise spacecraft, which is out there taking infrared images of stellar objects.
Yeah, whether it's going to be bright or not, it all depends on what the orbit is going to be like, right? And the closer it comes to the sun, the longer the tail, the brighter it is. And I think this other Neowise comet has a much a wider orbit. It doesn't come close to the sun,
right.
So it's not gonna unfreeze enough to put on a show. What?
Did you ever play for Blue Oyster Cult?
No, I did not play for Blue Oyster Cult. Yeah, well, He's much more talented than I am. Believe me.
Any other questions?
Let's see. I like the oyster call. Any other questions here? I think that's it.
All right.
People seem to have a good time. Thank you all for joining us. I can't wait till next week when we get to do it again.
Yeah, once again, we'll remind you about that auction. You should be able to see the link. John, were you able to post that yet?
I never got it because my email is
someone
else posted it.
Oh,
Yeah,
okay.
I saw that someone else posted it.
Okay. It might have been Jessica or Mary Catherine posted it. Anthony Chabot. Yeah. Okay. So that was Jessica or Mary
Thank you,
Catherine.
Jessica.
Yeah.
Yeah, our struggle is that we are managing this entire process in Zoom, and so it's harder for us to paste something into Facebook. So I'll have to figure that out.
So anyway, you want to check that out if you're interested. Also, if you just want to donate to Chabot, you can go to Chabot's website, chabotspace.org. You'll see a donate button up at the top of the page. Should be a donate button also on our Facebook page, I think just above the comment section. And all the support you can give us, we really appreciate. We're still continuing to do all the live streaming and various science programs while the facility is not open to the public, but we are working our way towards reopening in June of next year. That'll be our grand opening. And, in the meantime, we need all the support we can get. So please click on that donate button. All right.
Great. Thanks, everyone. Have a good rest of your weekend, and we'll see you again next week.